Hi everyone, welcome to my YouTube channel Networking Made Easy by T.S. Srinivas. So, in continuation with our series of communication basics, well, as usual, it's another very useful and important topic. It's nothing but introduction to digital communication. Okay. So earlier we have seen the communication was happening, how analog communication was happening. See, basically, if you see any information, basically it is analog. Okay. Analog means it's a time varying continuously at every instant some value is there. But whereas digital, it is discrete. Okay, when you listen to the word digital, always we know that we try to represent in binary, that is either 0 or 1. It is discrete. Okay. So, see, what is the purpose to go into digital communication actually? So, somebody might have got some idea what is the benefit of going into the digital communication. So, before going further, what is the advantages for the digital communication? Let's see how this particular digital communication works actually. So, it was originally introduced in the telecommunication, the digital communication. So the word which is very popular is the pulse code modulation. Pulse code modulation. Okay. So this is a simple block diagram. So you give the input analog signal. Okay. Basically the logic is that the input signal is given to the analog signal, and this is a low pass filter. So what is said to be that the low pass filter, it's a band limited. Okay. It is having a band limited. You are taking certain band of frequencies, means it is having a lowest frequency and the highest frequency. Okay. So that signal is being sampled. Okay. Sampled in the sense, see, you are collecting certain samples of the original signal. Okay. So see here, just I want to give some small idea. So especially when you were kids, you might have seen, okay, in the children magazines and all, you might have seen some big pictures like some birds, animals. So it is given into the dots actually. So the main figure is not clearly visible, just it's only the dots. So when you join this particular dots in a very sequentially, okay, so a new picture is forming. Okay, the original picture is, you are able to identify the picture. It is something like that. The original signal is analog signal, okay, but what you are trying to do is, you are trying to take some samples of this particular signal and you want to process it. Okay, so when you sample it, then you have to convert, means you have to sample means certain value. Okay, so this value you can easily represent in the form of a digital. Okay, so that's what the quantizing part is being done, and then it is encoded, and it is all these sampled values is represented into the binary. So you get a stream of bits. Okay, so what we understood from this particular thing is, the original signal is being sampled and we are trying to convert that particular values, whatever the samples you have taken in, you want to put into the digital format. So up to here it is okay. So now here you will come to know, so what is actually basically, so in this particular episode we will try to concentrate more on the sampling and the quantization. Okay. So basically sampling means, definitely question should come, how many samples you have to pick up. Okay. So that's sampling rate, sampling frequency should, so which will be equivalent to 1 by Ts. Ts is nothing but the sampling interval, because whatever the samples you are taking, between the two different samples you have a sampling interval. Okay, but the question is, how many samples to be taken? So the Nyquist is a person, he means definitely see anything will not come out just like that. Okay, so after making a lot of research or investigation, so many experiments have been conducted, then they found out that if any band limited signal, okay, if it is sampled, okay, greater than equivalent to 2 FM, FM is nothing but the maximum frequency available in the particular band limited signal. If you are able to sample twice that particular frequency, okay, if this particular samples, if you are able to process in the receiver, you are able to reconstruct the original signal. So that is what it is understood. Okay, after doing so many experiments, they have come to a conclusion that the sampling rate should be greater than or equal to 2fn, so that if it is done in this particular way, you will be able to recollect the original signal. So that was the logic. So you may get a doubt, if it is sampled at the lower side, what could happen? Okay. See, generally any analog signal, if it is represented in the frequency spectrum, okay, so it will be shown like this. Okay. Say if this is the signal which has to be sampled, okay, if it is sampled at the lower rate, less than the highest frequency, what could happen is, see, generally one thing you should understand, whenever you are sampling certain frequency, okay, it is nothing but you are multiplying with some samples. It's a stream of pulses you are multiplying with the original signal. So the result is, it will be generated like this. Okay, but our actual requirement is this signal. Okay, this particular signal. If you are able to get this particular signal and process it, definitely you will be able to reproduce the original signal. But if you are sampling at this rate, the spectrum is like this. Okay, so you can easily see that there is a overlapping at these particular places. So definitely the higher frequencies and the lower frequencies of the next spectrum is overlapping. So there is a loss of this particular signal. So you will not be able to reproduce the original signal. So that's the reason. So this is a big loss. You cannot. Okay. Now the next case, if you are sampling equivalent to highest frequency, then the result is like this. So this is good. Okay, to some extent it is okay. Now in this you will be able to remove it, okay, and start working on to that. You will be able to reproduce the original signal. Okay, but see, here also you can find there is a drawback, because getting such an ideal low pass filter is too difficult. It's very close. Okay, so there should be some adjustment, isn't it? Some tolerance. So it should not be neck to neck. So if you are slightly, doing it in a higher sampling rate, the result is like this. It is good now. Okay, now you are comfortable. There is a sufficient gap is available. Okay, now here you can have a low pass filter and take out the one and start processing it. You will be able to reproduce the original one. So this is fine. So that's the reason it is told that either it should be equivalent to 2fm or greater than that. Okay. Now see, it is up to us now to decide. It doesn't mean that, see, higher means how much higher. If you start taking samples much more than this, it is of no big requirement. See, how much gap you want to have. Our ultimate objective is just to take out easily. Further, there is no requirement. You do any amount, it's not having any meaning. So that's the reason it should be slightly higher than the 2fm. Okay. Now see, here itself you can understand. See, basically, if you have listened to my original, the first lecture, I told, see, because since the PCM is being introduced into the voice communication, the telecom, okay, you can understand already I told the voice frequency range, the bandwidth is say 300 Hertz to 3000 400 hertz. So ultimately the bandwidth is 3100 hertz. Okay, but I told in the telecom bandwidth allotted to for one voice frequency is 4 kilohertz. So reasonably we have given sufficient space. So I told, see, around you have 900 hertz extra, so it works like a guard band. Okay. So similarly, if you take this as our input signal, okay, so after band pass filter, if the cutoff frequency is 3100 hertz, okay, so you are getting this much of voice signal here, but you sample at double this. Okay, that is 8000 samples. Okay, so that is the effect. Okay, so this particular small gap is working, that guard band is being used. So it is not required. You no need to go to 9000 or 10,000 samples. There is no meaning because your purpose is solved at this particular place. Okay, so that's the reason. So in the sampling, if it is being done, this is followed. This is followed because see, that's what it is told here. The sampling rate should be slightly greater than or equal to 2 FMS. That's the reason. You could have done it at 6,200 itself, but you are going sampling up to 8,000. So small clearance is there so that you will be able to reproduce the original signal. So I think you would have understood what is the Nyquist rate and okay, how we are achieved to this particular requirement. Okay. So in fact, if you want to know, this particular problem is called as aliasing technically. Okay, fine. So once you understood this particular sampling concept, so there are different ways of sampling. So there are 3 methods of sampling. Okay. So this particular thing is called as an ideal sampling. So what has been being done is the samples are taken instantaneously. Instant. At that particular instant, whatever the value is there, that is taken. So that is the instantaneous, means that is ideal sampling. Means ideally, at that particular instance, whatever the value is there, that is taken. So these samples are being collected. Okay. So whatever the interval is there between the samples, that is nothing but the sampling interval. Okay. So that is okay. That is there in everything. So now see, the drawback is whenever you want to pick up the sample, you want to pick up instant. What is the particular value? See, there should be some time, isn't it? So it's very difficult to implement this type of sampling, ideal sampling. I mean, instantly, what is that particular value picking up? It's too difficult. Okay. So that's why it means we go for the natural sampling. So what we do here is we send a stream of pulses. Stream of pulse means it will have certain width. Okay. So this pulses is multiplied with the original signal. Okay. So this is something like this. So what is happening here is this is natural sampling. So the top is taking the shape of natural, how the signal is moving. You see, this is natural sampling. Okay. So see, again you will find some difficulty here. In this particular sampling period, in the small sampling period itself, if you want to take the value, because see, there is a continuously changing. So which particular value should be considered in that particular sample? There should be some single value, isn't it? So again, it's a troublesome in the natural sampling. Okay. So finally, we go for a flat top sampling. So this is being implemented in the PCM. Okay. So now you see here a stream of pulses so nicely. You just see. You take a sample and hold. Okay, that's it. And hold for some time. But note it down, isn't it? Somebody has to note it. You just stop. Okay, you stop and take the reading. So that's the thing. So you should have some time to note the reading. So that was not possible here. Okay. So we go for this. You take a sample, wait. So it is holding there. So you will have a single value. Okay. So this seems to be okay. Means if at all you want to take samples reasonably, then you are able to achieve this particular job in the flat top sampling. Okay. So up to here you might have understood what exactly is sampling, how you are taking the samples. Fine. Okay. So once you have taken these samples are given for quantizing. Okay. Now this quantizing is one interesting word, like because any value when you want to, again it is value means some level, some amplitude, some voltage. Okay, that voltage has to be represented into the binary form. Okay, if you want to represent in the binary form, you require certain digits to represent. Okay, so see, for example, certain value you are getting at one particular instance, some value, one sample. If you are taking 4 bits to represent, then you will have 2 to the power of 4, so that is nothing but 16. So you will have 16 levels, okay, fixed levels. See, for example, what I mean to say is, see, suppose this is varying between plus 1 volt and minus 1 volt. The whole signal is varying between these two values, then ultimately the result is actually the 2 volts. Okay, if these 2 volts, if you are dividing it by 16, okay, then you are getting each level is 0.125. Okay, so from 0.125, next level is 0.25. So likewise you keep adding, because okay, so that is what. So in between these values, if any signal is there, you cannot get that particular value. So here again I want to tell you one thing. We are all familiar with one term called round figure. Round figure, isn't it? Okay. So when you want anything difference, like you want to compare to either lower side or the higher side, which is closer. For example, if you take if you want to represent in the money, in the nearest figure, if you want to go, okay, 59 rupees 45 pies, then it is okay. You consider it as 49, because it's a general trend. If it is less than 50 pies, you ignore. If it is more than 51 pies or 52 pies, then you go for 50 rupees. So that's what is a round figure, because we are going for the approximation. Okay, so that is what is being done, because it's too difficult to represent that value as it is, because you are using certain bits. So you should have certain levels to represent, because the standard levels to represent the particular value. Okay, so it all depends. Now that's what. If you have 4 bits, it is 16 levels you will have. So each level value will be this much. Each step will be of this much size. And similarly, if you have more number of bits, like you have 8 bits, you have 256 levels. So the step size will be this. Okay. So why we have to talk about this is, so now whenever you are going for a round figure or something like that, now it is understood, because whatever sample value you are taking, you are straight away not converting to its equivalent, exactly equivalent value. Either you are going higher side or you are going to the lower side. It means there is some adjustment. So you have to agree that we are not following the original signal. We are not following the original signal. Okay. So definitely, if you are not following original signal, means there is a difference. So whatever the signal you are trying to reproduce at the receiver and with the original signal, there is a small difference. Okay. So definitely this particular difference, we call it as a quantization noise. It is a quantization noise actually. So we have to be very careful, because if the noise is more, then you will not be able to reproduce the original signal. So that's a drawback. So, in order to overcome this quantization noise, we have some solution like, okay, now here you see, just don't get confused with this particular big picture here. So many lines are there. I want to just explain you how your approach towards the quantization should be. Okay. So in this particular half picture, okay, this is actually we are doing as a linear encoding. We are converting. Okay, encoding in the sense means whatever the value is there, you are trying to represent in the digital form. So that is nothing but the encoding. Okay. So now here you see, okay, if you have 4 bits, you have 16 levels here. These are the different levels. 8 levels positive side, 8 levels negative side. And see, already you are decided that I have 16 levels fixed and the step size is uniform. It is linear, equal. Okay. Now here I represented 2 signals. Okay, this bigger signal which is passing through like this. Okay, this is a stronger signal. This is a stronger signal. And there is another signal. Okay, this signal is the weaker signal. Okay. Now just first you understand how the samples are taken. So whenever you want to pick up the samples from this particular bigger signal, you see a sample is picked up at this place. Okay. The next sample duration when it comes, it is falling because that time it is finding that it is at this place. So whatever value corresponds to this, so that value is taken. So next step again it is taking like this. So this it continuously follows. Okay. So when the signal is in this particular form, okay, there is no issue in the case of a linear because you are almost continuously following the original signal. Okay. But you see here, the problem comes when the signal is weak. Signal is weak in the sense when its amplitude is low. Okay, you just see the signal's amplitude is varying between 2 levels. 2 levels only. So that time what you take, when you have taken a sample value at this place, okay, then again it is not fallen. So either it should be on the top side or bottom side. So at this place it is changed to next level. Okay, now you see it is continued. This value being continued, okay, up to here. So it is lying very close to this line, so it has continued up to here. Then finally when you found it is changing to this side and it has changed. Okay, so you find so many samples which has been collected is means changing between only 2 values. So it's not right. Definitely you are not following the original signal at all. So if you are encoding with the linear encoding, so there is a drawback in the means in recovering the weak signal. So that's the reason. So it is going for the, it is okay done with the help of a non-linear encoding. So non-linear encoding, nothing big here. As it is, you have same 16 levels. Okay. So what you are doing here is your step sizes is not uniform. Choice is yours. It doesn't do any big damage. Okay. Now you see these levels same. It is ranging total 16 levels, but the spacing between these lines is different. Okay, so at this particular place where the amplitude is low, there you have more number of levels. You have more number of levels. So that is the reason. See, here when it is processed this weak signal, okay, you see at this place it has got one level, okay, and another level here. Immediately again. Okay, so you see where at this place in the linear encoding you are having 2 values. Now here you see how many values you are getting. Okay, so for the same duration you got so many different values. It means what? See, one thing you should understand, samples means if you collect more number of samples, whatever you are doing, if the samples are more, then you will be closer to original. Okay, so that is a simple logic. So that's what it is being done here. See, ultimately, see already the quantization error or quantization noise can be reduced in this way. Okay, so I'm sure you might have understood what exactly is the sampling and what is the quantization. Okay, so fine up to here. So I have not talked much about the encoding. So if you have understood the sampling part and the quantization part, and there is, so next session we will be discussing about the what is actually encoding and what is the concept of line coding. So we will discuss again PCM in detail in the next session. But as of now, you should have understood what is actually a band limited signal, what is actually a concept of sampling, okay, what is the Nyquist race, what is the importance of this particular rate, how it has been decided, okay, whether it should be equal to or greater than, and what is the problem if it is sampled at the less than 2 FM, okay, and similarly different types of sampling mode are understood, what is the quantization, the approximation, okay, closest. So if you want better understanding the round figure, like see in the linear coding and non-linear coding, see for example a simple logic, say for example you are going for purchasing a flat which is costing 52 lakhs, okay, so generally when you want to bargain, okay, you make it round figure. See, the round figure is again interesting. So you ask for 50 lakhs, isn't it? So 2 lakhs is removed. So it's a stronger. Okay. Similarly, when you go for a purchase of a product within thousands, you want to go for a LCD TV or something which is costing 82,000 or something like that. You ask for 80,000, isn't it? 2,000 it is reduced. And similarly, when the product is coming down to less than 1,000, it is in rupees. So accordingly, you go for bargaining for rupees only. So you cannot take the same yardstick for all the things, isn't it? All the products. It will be too difficult. So there is a logic. Okay, in the non-linear encoding, so this has been taken care. So wherever you are, accordingly, the levels have been adjusted. Okay, so this is what is the big advantage of a non-linear encoding, so that you can reduce the quantization noise as much as possible. Okay. So thank you. So we'll continue with the PCM in the next episode.